Okay, so today we're going to be talking about the calculations for Lab 10, which is acid-base titration. At the end of our laboratory video, we just finished the titration of a solution of taco sauce, which contains acetic acid, and we titrated this acetic acid with sodium hydroxide. We monitored the pH as a function of the volume of in this case, of sodium hydroxide. And the way that we determine the equivalence point using a pH meter is that you record the pH after every 0.5 mils, and then we plot pH versus the volume of citric acid. And the center point between our two inflection points, the points when our curve changes in slope from positive to negative, if we find our two inflection points, then we can calculate the pH at the equivalence point by taking the average of the pH at the two inflection points. So that's how we're going to find the equivalence point from our experimental data. Now let's talk more about how we can complete the goal of this experiment. What is our ultimate goal of the experiment? How is our data going to help us accomplish that goal? And how do we process that data? So our goal, what we're trying to determine in today's experiment that we just performed, the goal is to determine the concentration of acetic acid, which is CH3CO2H, in taco sauce via titration. Okay, so concentration in terms of molarity is defined as the moles of substance per liter of solution. So let's talk about how we're going to find each of these components. So in this experiment, we took our beaker and we transferred over 1 milliliter of the taco sauce, and we recorded the mass in grams. So we know the grams of taco sauce. Okay. Now, in terms of the liters of solution, in terms of the volume of taco sauce that we titrated, we know that we titrated roughly 1 milliliter of taco sauce. And we can use the density of taco sauce if we wanted to also calculate the volume. So you can also say volume is equal to mass over density. Both methods are acceptable in this case. Okay, now how do we figure out the moles? So in titration, the way that titration functions is that we use a reaction between a solution of known concentration that we call a standard solution. In this case, that would be our sodium hydroxide, and a solution of unknown concentration to determine the concentration of the unknown solution. So in this case, we have another chemical reaction. In this case, we have acetic acid, which is known as a monoprotic acid, 1 proton, reacting with sodium hydroxide, which is a monoprotic base. After reaction, you'll generate sodium acetate plus water. Okay, now putting in our coefficients for a moment, we can see a clear relationship between the moles of sodium hydroxide and the moles of acetic acid. How many moles of sodium hydroxide are required to react per mole of acetic acid? What is our mole to mole ratio looking at our coefficients? What's our mole to mole ratio? What is our mole to mole ratio? 1 to 1, exactly right. So we have 1 mole of sodium hydroxide per 1 mole of acetic acid. And we have a special term called the equivalence point. And the equivalence point is the point in a titration when the reagents are present in stoichiometric amounts. So it depends on the reaction equation. In this case, it would be 1 to 1. So for this reaction, the moles of sodium hydroxide are equal to the moles of acetic acid at the equivalence point. Okay, now we can write moles in terms of concentration. Molarity is defined as moles over liters, or N over V. And so we can rewrite and solve and say that the moles of sodium hydroxide are equal to the molarity of our sodium hydroxide times the volume of sodium hydroxide added. While the moles of acetic acid are equal to the molarity of acetic acid. This is what we're after, so let's put a star next to it, times the volume of acetic acid solution. And we know that this is the volume of about 1 ml. That's how much taco sauce we titrated. Okay, so now from this idea, we can very clearly solve this equation and show that the molarity of acetic acid is equal to the moles of acetic acid. Well, let me rewrite this. So plugging in these mole expressions, we can see that the molarity of sodium hydroxide times the volume of sodium hydroxide is equal to the molarity of acetic acid times the volume of acetic acid. In other words, the molarity of acetic acid is equal to the molarity of sodium hydroxide times the volume of sodium hydroxide over the volume of acetic acid, which we know is about 1 ml. So the question becomes, how do we figure out the volume of sodium hydroxide at the equivalence point? Well, looking at our equation, we know that at the equivalence point, the pH is equal to the pH of a solution of sodium acetate. Now, past the equivalence point, the pH will change as excess sodium hydroxide is added. So to talk a little bit about how that works in terms of titration curves, let's show a titration curve. So pH less than 7 is acidic. pH greater than 7 is basic. pH equal to 7 is neutral. Now, if we look at a titration curve shows the pH as a function of the volume of sodium hydroxide in this case. And we know that as sodium hydroxide is added, the pH increases. So initially we start with a pH around here. Our pH is going to increase, increase, increase. And then you'll see this sharp jump. So this sharp jump indicates we are approaching the equivalence point as acid is being consumed. So to help you understand a little bit about how this works. So initially, in our initial stage of our titration, the moles of acid are way greater than the moles of base. So as a result, the pH does not change substantially. The pH is based on the log of the concentration of acid, or more formally, it's based on the concentration of H+. So initially, our pH is not changing very much. However, near the equivalence point, the moles of acid are very close to the moles of base. So the pH changes as base is added. And then at the equivalence point, the moles of acid are equal to the moles of base, and the pH changes rapidly. Now, that's all fine and good. The key point that I want you to take away is that the equivalence point is the point where our pH changes the most rapidly. And we can measure the equivalence point by identifying our two inflection points. And our inflection points are our points where we change from concave to convex. So this would be one inflection point. So we'd record this pH. So this would be pH 1. And then we record the pH of our second inflection point. So here's our other one. That would be pH 2. And our equivalence point is the average of our two inflection points. So our pH equivalence is equal to pH 1 plus pH 2 divided by 2. Now, the goal of this entire process of identifying the inflection points and measuring pH as a function of volume is to determine the pH at the equivalence point so we can determine the volume of our equivalence point. Then what we do is we plug it back into our equation for the concentration of acetic acid, which is equal to the molarity of sodium hydroxide that we established to be 0.1 molar times the volume of sodium hydroxide at the equivalence point over the volume of acetic acid solution, which is 1 ml. So what we're going to do next is we are going to generate this plot we're going to identify our inflection points. And after we identify our inflection points, we will solve for the concentration of acetic acid. Does that make sense to everyone, what we're doing right now? Any questions so far? Any questions? If not, let's begin processing our data to determine and identify our equivalence point for this titration. So let's now pull up Microsoft Excel or Google Sheets. I'll be doing this in Excel just for consistency's sake. So let's share our Excel sheet. And I'd like you ideally to be following along with me in Excel. So that way we don't have any issues with this plot. So first and foremost, let's make a plot of the volume of sodium hydroxide. And the volume of sodium hydroxide will be in milliliters. Okay. And so that'll be, the volume of sodium hydroxide will be our x-axis. Our y-axis will be our pH. So what we're going to do first and foremost is at 0 milliliters, what was the pH of our acetic acid? We recorded that as 4.44. So we're just transcribing our data points. After 0.5 milliliters of sodium hydroxide, what was our pH? What was our pH? .81, okay. After 1 milliliter, our pH, oops. After 1 milliliter, our pH was 4.86. After 1.5, it was 5.27. After 2, it was 5.28. So we're just entering the data we collected in the lab recording. So let's enter our data exactly as we have it from our lab notebook. And I'm just going to use some Excel shortcuts. So here's our whole data set, exactly as you should have seen in your laboratory notebook. So now from this data set, what we're going to do is we're going to plot pH versus volume. So we're going to highlight our whole data set. Oops. Now we're going to go to Insert, and you're going to click on the little scatter plot button. So we should end up with the following plot. Oh, whoops, it's in reverse. Sorry, you want to have your volume on the left, sorry. Okay, since we're plotting volume, we're plotting pH versus volume. Okay, so let's, whoops. One moment. Cell got a little bit confused. So we're going to plot pH versus volume. So your volume of sodium hydroxide is going to be on the x-axis, and you're going to plot a scatter plot. So your plot should look something like this at first glance. You're going to click on the Add Chart element. You're going to add axes titles. And from here, we're going to modify the title. So pH versus volume of sodium hydroxide milliliters for titration of taco sauce with 0.1 molar sodium hydroxide. Okay, for our axis titles, for our x-axis, we're going to put the volume of 0.1 molar sodium hydroxide in milliliters. And for our y-axis, we're going to put the pH. So is everyone at this point in their procedure? Is everyone at this point in their procedure? How's everyone doing so far? Okay, so from scratch, you're going to highlight your data. You're going to click Insert. Then you're going to click on the little thing with a bunch of dots, scatter plot, and you're going to insert a scatter plot. Then you're going to add chart elements and add an axis title. And that's it. Does that make sense? So now that we have this chart, and this is perfect for what we need, you're going to look at this chart and you're going to identify the point in which your curve changes in slope. So let me annotate really quickly. So let's switch this to full screen and let's make this really large. So let's annotate here for a moment. Okay, so does everyone notice how the curve initially looks like this, right? And beforehand it was like this. So do you notice it was concave, now it's convex? So this would be an inflection point. So we'd use the pH for this value, which is 9.55. Is everyone following along on their graph? Does everyone notice this inflection point in their data? It won't always be at the exact same pH, but it should be in the general range. Does everyone else see in their graph an inflection, one of their inflection points? Okay, so in the second part, so for our second inflection point, our curve is convex and now it's concave. So this point right here is our second inflection point. It's a little tricky to tell for this one. So it has a pH of about 6.79. So our pH at the equivalence point, averaging them together, would be 9.55 plus 6.79 over 2. So let's do that really quickly. So we have 9.55 plus 6.79. Then take this answer divided by 2, and that gives us a pH of 8.17. Okay. I'm going to draw using Microsoft's features. So again, just to clarify, so using the draw feature, this is point 1, which has pH of 9.55. This is inflection point 2, which has a pH of 6.79. The pH at the equivalence point is the average, so we take 9.55 plus 6.79, divided by 2, which gives us a pH of 8.17. Now, what do we do with this information? What do we do with this information? Well, what we're going to do is we're going to click on our data points. I'm going to go to Format, Plot Area. Oops, let's double click on this plot. None of the options work very well for this. So what you're going to do next is, now that you know the pH, what you're going to do is you're going to extrapolate your curve. So our pH is slightly above 8. And we're going to extrapolate our curve to the point of the point in your chart. So you're going to identify your pH, you're going to trace it to your chart, and then you're going to go all the way down. And you're going to record the pH at you're going to record the volume at your equivalence point. In this case, from this chart, after extrapolating from our pH of 8.17 to our curve and down to the volume at our equivalence point, the volume at our equivalence point looks to be about, and this is approximate, about 3.8 mils. Any questions on this example? Any questions on this example? Any questions on this data analysis? Did everyone get a similar result for their titration? Not identical, but did everything? Oh yeah, That's because I'm using a surface. But what I would do is you don't have to necessarily draw in Excel. I'm not looking for any of this drawing in your final submission, but I do want you um, to be able to, in your laboratory notebook, note the 2 inflection points, show this pH calculation, and then show, or at least explain, how you determine the volume. So you may have to print it out or do it by hand. I'm just drawing on it to show the exact process of how you'd extrapolate and determine the volume at the equivalence point. Any other questions on this example? Is it making sense so far?
Wait, so how did you get the volume equivalence of 3.8?
So once I determined my pH at the equivalence point, I went from my pH, my y-axis, I traced it into my curve of pH versus volume. And then once my line going from my pH intercepts my plot, I go down and I extrapolate to the volume, and I just read off the volume from my graph. Okay. So in this case, this volume is about 3.8 mils. Does that make sense?
Yeah.
So now that we have this data compiled, let's go back to our calculations. Let's share this. Let's share our OneNote page, and let's now complete our calculations for this experiment. So in this case, the molarity of acetic acid is equal to 0.1 moles of sodium hydroxide per liter times 3.8 milliliters of sodium hydroxide over 1.0 molar, 1.0 milliliters of acetic acid times 1 mole of acetic acid per 1 mole of NaOH. The milliliters cancel, the moles of NaOH cancel, and we're left with, for our molarity of acetic acid in our taco sauce, as about 0.38 molar. Given our molarity was provided to 1 sig fig, we round this to 0.4 molar. So this is the approximate molarity of acetic acid in taco sauce that we determined in this experiment. Does this make sense to everyone? Are there any questions? So I'll give everyone a few minutes just to look over the Excel sheet. And if there are any questions, really don't be shy to ask. And if there's any part that you'd like me to explain further, let me know. Any questions so far? For those who collected their own data set, are your calculations looking pretty similar?
Is it okay if I copy and paste the graph to the lab and then explain there the...
Yes, yes, you're more than welcome to. Mhm. Are the calculations going okay for everyone?
On the side of your graph, it says 16.34 and 8.17. What is that?
That's 6.7. Yeah, this is the calculation of the pH at the equivalence point. So let me just make that clear. So the pH at the equivalence point is the average of the two pHs from our inflection points.
Okay.
So the pH at the equivalence point is equal to our first pH, which we read off from our graph to be 9.55, plus our second pH from our second inflection point, which was 6.79. If we add these two numbers together and take the average, we get a pH at the equivalence point of 8.17.
Okay.
Any questions on the calculations for this laboratory? Any questions on processing Excel for this laboratory? So from this, you have all the information you need to complete the calculations for laboratory 10, the titration of taco sauce with sodium hydroxide.